That's in the eye of the tongue of a taster, I guess. All right, so I have here, this is the solution to the practice final. So if any of you have had a chance to look at any of it, are there any problems in particular that you'd like me to take a look at first?
Is there 15 questions on the test or 20?
There are 15.
Okay.
Yeah. Oh, did it say 20 in the practice? Okay, yeah.
There's 15 problems, so I didn't.
Yeah, because I think the last time I taught this class I had 20, but it really is going to be 15.
Okay.
So, actually, let me make absolute certain on that and just open the thing up. Come on. Oh, wait. Oh boy. That's weird, because when I open up the practice test on my laptop, it says correctly there are 15 problems. So I better make sure at least the problems themselves are the same. Because I wonder if I fixed that mistake and then didn't re-upload that. But I think the problems are the same. Let's see, and yeah, the formula sheet, all that's there. Okay, so the only discrepancy between one that's posted and the one on my laptop is just the language in the first page. And then when I look at the real test, just so we're literally on the same page here. Oh, whoops. Fair enough, there are 15 problems, but in the real test, I forgot to include a formula sheet, so I need to attach that. And it says on the first page, there are 14 problems, but there are 15. Okay, so the way it would work, so I need to address both versions. So since 100 is not divisible by 15, so I'm going to make each problem worth 7 points. So that's a maximum total of 105 points if you get all 15 problems correct. But I'm still going to count as out of 100. So that gives you a little edge. Okay. Now that we're all clear there being 15 problems, are there any one of those 15 that you'd like me to discuss first? Okay. Yeah, because if you all conclude are equally miserable, then I'll just...
Yeah, we can just start from the beginning, I guess.
Okay. We have the first 5... No. The first 7 problems deal with older stuff. Although you never got a test problem on Lagrange multipliers. Okay, so 4. Okay, well that is one of the older problems. Okay. All right, so this double integral you're given. So the region D is bounded by y equals 0, y equals the square root of 3x, and just to be clear, only the 3 is under a square root sign, not the x. So this is a line, and the slope is square root of 3. And a circle, x squared plus y squared is equal to 9. This is a polar coordinates problem, which is you can be tipped off to that by the fact that the domain is of integration is part of a circle or a disk. Okay, so we have y equals 0 is one boundary, y equals the square root of 3x, and then you have this circle of radius 3 defining. All right, so this segment is of length 3. Okay, so this region I'm shading here is your region D. Okay, so by using polar coordinates, we can get simpler limits than what we would get. Because if you just stick with dx and dy, you'd have to break this up into 2 integrals. You'd have to divide it right here. You have to figure out this intersection point, and then you have one integral with the line as a top boundary, and the other integral with the circle as a top boundary, and your lower limit always being 0. But if you use polar coordinates, you can do all this in one integral with constant limits instead of variable limits like you would have in the dx dy case. So use polar coordinates. So x is r cosine theta, y is r sine theta. And just as helpful in this problem especially are how you go the other way. R is square root of x squared plus y squared. And tangent theta is equal to y over x. And so I want to check here on the formula sheet. And, okay. Yeah, well, I don't have polar coordinates, but I have cylindrical, which includes polar. So these formulas are on there. It's just, you have also z equals z to make it cylindrical. Also, I just want to make sure that there's no mix-up. On the practice test that you downloaded, it has a formula sheet in it? Okay, all right. So that's what you'll have. Now, so we have to deal with this integrand, right, in polar coordinates. We have to come up with the limits in polar coordinates. So we need to have inequalities. R is bounded by something. Theta is bounded by something. And then the Jacobian, or that's the extra factor. What is the extra factor for polar? It's just R. Okay, so that part is straightforward. Okay. Now, let's deal with the integrand. So what's the what is this going to become? This whole thing?
R squared.
The inside is r squared, and then we raise that to 3/2 and get
R
cubed.
no,
No,
r. Well, r cubed, and then the extra factor of r.
So also 4.
Yeah. So this whole thing is r cubed. So we'll have r cubed as our integrand, and then the extra factor of r, dr d theta. So yeah, the overall integrand will be r to the 4th. So that 3/2, a similar thing came up on test 2. So when you see that 3/2, that's something you can expect. That whatever's inside is going to be some perfect square, and then you raise it to the 3/2 power, and now it becomes cubed. Okay. Now, as for limits, well, first of all, what are the limits on R?
0 to 3.
It's 0 to 3 because we start at the origin and we work our way out to a circle of radius 3. Okay. Now, the tricky part, I don't know if this is what you have trouble with, how to get the limits for theta.
0 to 2 pi.
What?
0 to pi over 4.
It's not pi over 2 and it's not pi over 4 either. Okay. Well, it is 0. It is, okay, this line, y equals 0, is also theta equals 0, so that is your lower limit. Now, to get this relationship actually helps. Tangent theta is equal to y over x. So here, along this line, tangent of theta, which is y over x, but on this line, y over x is what?
Square root of 3.
Square root of 3, the slope. So, if you have some boundary of your region that's a line, y equals mx, in polar coordinates, that means theta is equal to arctangent of whatever your slope is, m. So for instance, if this had been a line y equals x, which has occurred in some examples, then that's theta equals pi over 4, because that's arctangent of 1. But here so our upper limit is going to be arctangent of the square root of 3. But now, okay, you can do that on your calculator. I'll show you how you do that without a calculator, because I picked a nice value that can be done without a calculator. How do we define tangent? Tangent is
Sine
sine over cosine. So you want this to be square root of 3, but if I think this is a fraction, like that would be the same as square root of 3 over 2 over 1/2. And these are values of sine and cosine that you would know, because square root of 3 over 2 is sine of what angle?
over 2 over 4.
Degrees or radians, I don't care. What? Pi over 3, or 60 degrees. Yeah, but we want radians here. So pi over 3, and 1/2 is also cosine of pi over 3. So your theta limit is pi over 3. Okay, so if you have y equals mx, you take the arctangent of m, and that is your theta value. So now we have our limits, 0 to 3 in r, and 0 to pi over 3 in theta. Okay. So any questions about the setup? So this is one of the ways in which nefarious calculus 4 teachers make polar coordinate integrals interesting, is to introduce a boundary like that. And I think, yes, this will get them, because we're that evil. We're so evil that we tell you how to do it. Well, I do anyway. But, okay. And I assume, therefore, that you can take it from there as far as the actual evaluation of the integral. All right. Okay, any other problems in particular you want to look at? Because we have 15 altogether, and we'll have Friday as well. But that may not necessarily be time to cover each and every one. So, however you want to prioritize. Okay. Hold on.
Yeah.
Okay. Well, I'm going to pick out, and if you think of one later, then by all means shout it out. I'm going to pick one. Whoops. Okay. That was not previously seen on a test on Lagrange multipliers. Okay. So this is the first one. Find a point on the circle, x squared plus y squared is equal to 4. So circle radius 2. Closest to the point 1, 5. So, and it's the problem says, I didn't write it down here, well, using Lagrange multipliers. Okay. So the idea is, a problem involving Lagrange multipliers is where you're trying to find a minimum or maximum of some function. In this case, it's a minimum because we're trying to make distance as small as possible. And you have some constraint. So if the functions themselves are not given to you as formulas, which they're not in this case, then you have to come up with them based on what the problem is saying. So here's what you need. First, an objective function. And this is a two-dimensional problem, so it'll be f of x, y. And that is a function that you're trying to minimize or maximize. Now, some problems ask you to find both. You find a minimum and a maximum, subject to some constraint. But in this case, this problem, we just want them in. Now, so the question you have to ask yourself is, based on what the problem is saying, what are we trying to make as small as possible? Just based on the wording. What needs to be made?
The distance between that point and the and that 1.5. 1 and 5.
Yeah. So f of xy is the distance between x and y and 1, 5. Now, so you use a distance formula. So that's a square root of the sum of squares. Now, just for convenience, if you're trying to minimize distance, it's equivalent to minimize distance squared. So that's what I'm actually going to use for my f, just to not have to deal with annoying square roots. So what you would get is x minus 1 squared plus y minus 5 squared. So that is the objective function. That's what we want to make as small as possible. Okay.
Was that given in the problem?
This formula? No. It's not, the formula wasn't given. It's implied by the wording. So it's saying, find a point closest to 1, 5. So the point would be some generic point xy that you're trying to solve for, and this phrase is what suggests what the function is. So it's applied in the question, if a formula is not given, what it is you're trying to make as small as possible or large as possible. Okay, so any questions about getting the objective function?
And what is that called? Like that function? Is there, you said like the shortest distance or?
Well, it comes from a distance formula. Yeah, so this comes from the distance between a generic point x1, y1, x2, y2 is this. Okay. And then similar formula for 3 dimensions. Okay. Yeah, so if a problem is talking about distance, then that's your typical of this is going to come into play. So that's one item you need to set up this problem. The other problem is the constraint. Function g of xy, which is something that limits the choices of x and y. And we write it in the form g of xy equals 0. So we want to have everything on one side. Because if we only had this, if we had no constraint at all, obviously the point that's closest to 1, 5 is 1, 5. And then we'd be done. The f of xy would be 0. But we can't just pick any xy. We have this equation. So there's going to be some equation that limits where you can choose xy from. Because it says, so this is a key phrase right here. Find a point on the circle, and then the equation for that circle is given. And that indicates what other equation x and y have to satisfy that's independent of this one. So that would be x squared plus y squared minus 4 is equal to 0. So this is your constraint. So the information is there in the problem, just whether it's given as a formula or in words. Is there any questions about getting these essentials? Now, for a unconstrained max or min, you'd only have this objective function, and you would take the gradient and set it equal to 0. With Lagrange multipliers, we don't do that. So now your critical points satisfy this equation. The gradient of f is equal to, well, this is a case of one constraint, which is what we have in this problem. Lambda gradient of g, which can be written as fx equals lambda gx, fy equals lambda gy. So then you have these two equations to solve, and you also have a constraint equation that has to be taken into account. So that's what would happen if you had one constraint, which is what applies in this problem. If you had two constraints, like g1 of xy equals 0 and g2 of xy equals 0, then you'd have gradient of f is equal to, you'd have two Lagrange multipliers. So you have one Lagrange multiplier per constraint. So you'd have gradient of f is lambda 1, gradient of g1, and then these are added together. Lambda plus lambda 2, gradient of g2. And you can see how it generalizes if we have even more constraints, which I would definitely not do. Okay. So these equations, together with your constraints, are what you need to solve for x and y. Now, you don't have to solve for lambda. And if it comes out, whatever. But really, x and y is what you need. Okay. So, okay, so let's get our gradients. Okay. So we need df dx, df dy. So what are the partial derivatives of our objective function? So with respect to x.
2x.
What? Yeah, this one right here.
Oh.
Anybody? Yeah, so 2 times x minus 1, or 2x minus 2. Okay, and then with respect to y,
2 times y minus 5.
what?
2 times y minus 5.
Yeah, remember my hearing sucks. Okay, yeah, so that's a gradient of f. All right, and then gradient of g. Okay, well that's so uninteresting, it's kind of sad. So 2x and 2y. Okay, so now the gradient of g we multiply by lambda and we set equal to the gradient of f. So now we can have all three of these equations that we need and then figure out how to solve. So from gradient of f equals lambda gradient of g, so we solve. Okay, so we have 2x minus 2 gives you fx, 2y minus 10, that's your fy, is equal to lambda times 2x, lambda times 2y. So this is fx, gx, fy, gy. And the derivatives of g are scaled by lambda. And then don't forget your constraint equation, x squared plus y squared is equal to 4. Okay. Now, what you can do is, what you do from here is highly problem dependent. Okay, let me make sure there are no questions about the setup. Because any Lagrange multiplier problem, you're going to have a system of equations like this. But what you do depends on the functions involved, as far as what is the easiest road to take algebraically. One thing you can do, this is a common strategy, is you can use these to solve for lambda, because from these two equations together, you get lambda. This is particularly useful if you only have one constraint. Lambda is equal to fx over gx from this equation, but it's also equal to fy over gy. So you get two distinct expressions for lambda. And at this point, you don't even care what lambda is, I think, as a number. In many problems, you would actually never find it. And it's not required. So now we can fill these in. So we have 2x minus 2 over 2x is equal to 2y minus 10 over 2y. Well, actually, we can simplify quite a bit. We can cancel 2's everywhere. So x minus 1 over x equals y minus 5 over y. So both of these are equal to lambda, and you can use these to get some relationship between x and y, which helps you to eliminate one of them. So let's cross multiply these, because fractions are a pain to deal with. So we have x minus 1 y equals x times y minus 5. And then if you go ahead and multiply everything out, so that's convenient because the xy's cancel. And so you're left with this relationship. Y is equal to 5x. So that lets you eliminate y. But now that we have this information, this doesn't help you get x or y individually. It just shows how they're related. So if you can figure out x, then you have y. So what should we do with this? Plug it into the constraint. So use all your equations. You need all of them to narrow down to a unique solution. So I'll substitute y equals 5x in here, so that's going to give us x squared plus 5x quantity squared is equal to 4. So that means 26x squared is equal to 4. And now you can go ahead and solve this equation for x, and you get two solutions because it's squared. So don't forget the positive and negative square root. And all right, so at this point you need a calculator because I just made these numbers up. So of course it wasn't going to work out nicely. Okay. So now that you have x, you can substitute that back in here and get your y values. So I can take those x values, multiply them by 5, and get plus or minus 1.96116. Okay, so now we have two candidates. So xy is equal to, first from the positive square root, and then from a negative square root. Okay. Oh, there's a minus for that one. Okay, so both positive or both negative. Okay. Are there any questions about how these were obtained? How do we know which one's the right one? Yeah, which one is closer to the point 1, 5? So now there are two ways you can do this. So, okay. So we can compute the distance f of xy, or distance squared. Okay. Or there's a way to figure it out in this particular problem without actually computing anything. Because you keep in mind you have this circle of radius 2. Your point is going to be on the circle. So one of these points is going to be like right around here. The positive square roots, and then the one with the negative square roots is going to be opposite. But the point 1, 5 is going to be up here. So you can see from a picture which one's going to be closer. It's going to be one to the positive values. So this one is the closest to a point 1, 5. So sometimes you can see this intuitively and not have to actually plug things in like crazy in your calculator. Okay, so any questions about this problem? So get your objective function, get your constraint, take your gradients, set up your equations from those gradients, how they relate to each other. Don't forget the constraints. And then you need to bring your algebra A game to solve these equations. Okay. Now, we have a fair amount of time. Is there any other problem someone wants to ask about? I guess we're picking one that's from the newer material. Okay, well, this is one that I think you've had something like this recently on homework. And certainly between now and Friday, think of, well, sure start looking at this and see what problems are the scariest. Okay. This one's number, no, not 10, 11. So this is close to get to any kind of proof that so gradient squared, if you will, but I'll explain that notation in a minute. The problem does too. Of f times g is g plus g squared f plus 2 gradient of f dot gradient of g. g. And these are f and g plus your functions of x, y, and z. Now, to explain the notation, this what looks like a gradient squared of f is really the divergence of a gradient of f, which is the same as fxx plus fyy plus fzz. We've seen this before. This is called the Laplacian of f. This right here, this is a dot product. So this expression in parentheses, gradient of f dot gradient of g, you take the gradient vectors for each, and you should know by now what the dot product is. You multiply corresponding components and add them up. Okay, so what you get is fxgx plus fygy plus fcgz. At this point, if you don't know your dot products, I think the punishment should be you have to take Cal 3 and this class again. Okay. So what do you do with a situation like this? Yes, and you will have one problem like this where you have some sort of vector calculus identity to prove. This one especially, you're just doing product rule until long past the cow's coming home. So from the fact that this is Laplacian, what you do is to start with one side and work out what it is and hope it becomes the right side. So it makes sense to start with the left side and make sure and see that it really is equal to the right side. So this symbol here, and this notation is given in the problem. So anything like that will be given. That's the Laplacian of f times g. So based on this definition here, that would be fgxx plus fgyy plus fgzz. So now you have to take the second derivative of a product. So you can think of it as applying a product rule twice. But there's actually a shortcut. This is a rule that's good to know anyway. All right, so if I wanted just a first derivative with respect to x, that's a straight product rule. So that would be gfx plus fgx. Now, if you apply the product rule twice and you get fgxx, and in this problem we only need to do it with respect to the same variable twice, you could go ahead and do product rule on this again, or you can remember this. This is g times the second derivative with respect to x plus 2 gxfx. So here you have a first derivative of both. And then you have fgxx. It's kind of like when you're expanding 1 plus x to a given power, because here you have the coefficients here are 1, 1. The coefficients for this one are 1, 2, 1. That's a pattern from Pascal's triangle. So for instance, if I wanted the third derivative of fg, I'd have gfxxx plus 3 gxfxx. So I'd have coefficients 1, 3, 3, 1, and that pattern will continue. So this one seems to come up fairly often, where you need the second derivative of a product, so it's worth knowing. So if you apply that here to each of these, what are you going to get? You're going to get g, okay, so this one's worked out already, so let's repeat it, plus 2gxfx plus fgxx. And then the same thing with respect to y and z. So gfyy plus 2gyfy plus fgyy. And then again for z. So gfzz plus 2
GZFZ plus FGZZ. So now everything has been, all the differentiation has been carried out. But now you have to group these terms in order to condense it into what's on the right side here. So for instance, notice there's an F here. And anywhere else in the right side, F is being differentiated. So if you just look for a plain old F, what terms have just F by itself? That one, and that one. So you group those all together. So you get, so basically you're writing these terms in a different order. GXX plus GYY plus GZZ. That covers this term. Then you look for all the terms that have just a plain old undifferentiated G in them. I'll circle those. That one, and that one. So you have G FXX plus FYY plus FZZ. And then what's left? All these terms that have a coefficient of 2 in them, you can factor out to 2, and you have FXGX plus FYGY plus FZGZ. And now we can condense all this because what is this? If you have all the second partial derivatives with respect to the same variable twice, all added up, that's that Laplacian of G. Then we have G times the same expression applied to F plus 2 times all this. And what do we have here? This you can recognize as a dot product. You have certain things multiplied together and then all of them added up. So this is dot product of Fx, Fy, Fz dot Gx, Gy, Gz. But that is the gradient of F, and this is the gradient of G. So we're being dotted together, and that completes the right-hand side. Okay. So, but for this kind of problem, it's important to be able to use your divergence and curl. Now, formulas for the divergence and curl are given on the formula sheet. Now, here the curl wasn't used. The divergence was basically used here because gradient of F is Fx, Fy, Fz. But what? And this is the divergence, where you differentiate each component with respect to the corresponding variable and add them all up. So if you use the formula for divergence in the formula sheet, this is what you would get. But it's something that's good to know that if you have a divergence of a gradient, it's just this. So you can jump straight to that if you know it. Yeah, so yeah, you're going to have this one divergence and or curl problem to show some identity like this. Any questions on this one? Okay. Okay, I can talk about the setup of, I'll just pick out the very last problem. Number 15. Divergence theorem one, like I was doing on Monday. Now, and it says use the divergence theorem on this integral, surface integral of a given vector field over a given surface. The vector field is x cubed, y cubed, z cubed, and the surface is S is bounded by, okay, so it's x squared plus y squared equals 1, so it's a cylinder, and with boundaries z equals 0 and z equals 2. So you have this z equals 2 is the top of the cylinder. So the surface is S, the interior is E. The divergence theorem says this integral is equal to an integral over the interior of this cylinder of the divergence of F. Now, what is the divergence? That's going to be x cubed with respect to x plus y cubed with respect to y plus z cubed with respect to z. So that works out pretty nicely. So that's just going to be 3x squared plus y squared plus z squared. But now what you need to do is, what coordinates should you use?
Polar.
Polar, and because there's a z, cylindrical. So you leave z as is. So the way you describe a solid, you need bounds on r, theta, and z. So based on the equations given here, what are the limits on r, theta, and z going to be? Oh, first for r. Basically what's over there tells you.
1.
Yeah, 0
0
to
to
1.
1.
Okay, theta?
0 to 2 pi.
Yeah, go all the way around 0 to 2 pi. What about z?
0 to 2.
Yeah, it's in the problem. The answer, the info you need is there. So now, you're going to have 0 to 2 pi in theta, 0 to 1 in r, 0 to 2 in z. Your integrand of the 3 I pulled out, and you just have, well, x squared plus y squared is r squared, so you can condense that. And then you still have plus z squared, and you have dz, dr, d theta, and what else do I need? R, your extra factor for polar or cylindrical coordinates. And then you can evaluate the integral from there. So it says divergence theorem, you're given a surface integral, and take the divergence of your vector field, and now you're integrating over the interior. You're not having to come up with parametric equations for a surface just because you're given a surface integral. Everything is done with the interior. So you figure out what's the most convenient way to integrate over E. Because if you have to do the original surface integral, you have to do the cylinder part, and also the bottom z equals 0, and the top z equals 2, and integrate over 2 disks. It would take 3 integrals. So it's certainly easier to do it this way. Okay. All right. Well, it's 12:50. So think of more problems, whichever ones terrify you the most, and we can talk about them on Friday.